most of the answers in Bjork-Mandrell or any other textbook if you want to look for them. However, I think you will find it more instructive to try and work them out just from the material in the lectures. That's a suggestion, not an order. On the problems in general, you are encouraged, if you cannot work them out by yourself, to search the literature, ask another student how to do it, anything like that. Doesn't matter. Now, are there any questions about the last lecture? Yes, sir.
Can you go over the motivation that they try to give us at the end for introducing the response field?
Okay, sure. Can I postpone that? If there are more technical questions, I will answer them first and launch into that later. Are there any other questions? Well, the general idea, as explained at the end of last lecture, was that if we have two space-like separated regions, space-like separated means there's no way for light to get from one of those regions, any point in one of those regions to any point in the other. And then we cannot say that an observer, which we idealize as being localized in the space-time, as being restricted to the space-time region R1, can measure everything, nor an observer localized in the space-time region R2. Indeed, there must be a powerful restraint between the things they can measure. If O1 is any Hermitian operator that can be measured by someone in R1, and O2 is any Hermitian operator that can be measured by someone in R2, they must commute. For otherwise, a measurement made by the observer in R1, followed by a measurement made by the observer in R1 could interfere with a measurement made by the observer in R2, and thus lead to the transmission of information faster than the speed of light. Are you with me so far? Now, so far we have just talked this, so we have to find, in order to find out where things are, in order to find out where we are, let alone where the meson is, where we are, we have to have some rule for associating observables with space-time regions. Now, in classical physics, there is such a rule, not in classical particle mechanics, but in classical field theory. The classical fields, there may be many of them, I'll label them by an index A, are functions of space-time points, and what an observer in R1 can measure are simply functions of the fields where the argument x lies within R1. He can measure things like averages of the fields over some subregion of R1, or averages of the squares or cubes of the fields, or things of that sort. Therefore, in this lecture, in the first part of this lecture, we are going to seek for a field, a density of observables, if you will, a thing which, when integrated, gives you observables, in quantum mechanics. But of course, observables in quantum mechanics are not numbers, they are Hermitian operators. So I want this to be an operator-valued field, an operator, or operator density perhaps, associated with every space-time point. And we want it to commute for space-like separations, so the observables constructed in accordance with the words I have said, and which I wrote on the board more explicitly at the end of last lecture, will commute if these are space-like separated regions. Is that a satisfactory answer, or do you want more details, or do you want to attack me at a point? Or? Okay, that's the physical motivation for looking for fields. Okay. I'm not saying that fields are the unique way of associating observables with space-time regions, but they're certainly the way that it is done in classical physics, and therefore the obvious way to try. If we can't do it with fields, we'll have to think again. We will be able to do it with fields, though.
You can measure fields only within the region
where you are.
Where you are. That may tell you something about another region.
But if you know the equations of motion and things like that, but by direct measurement, you can just measure the fields within the region where you are. Okay? Of course, in the case of classical physics, the electromagnetic field within this region enables you to deduce quite a lot about the electromagnetic field in other regions, but that's because you know Maxwell's equations.
I noticed that we've already encountered operator value field.
In p-space,
Yeah.
the annihilation.
Any help at all?
Yeah, we're going to build them up out of Fourier transforms of those. Okay, the annihilation and creation operators are themselves operator value fields in momentum space, not in position space. Okay? Now, okay, what I'm going to do is write down a condition we want our fields, or a set of fields, to satisfy so that they give us a definition of locality. I'll write down a set of conditions. Some of these conditions will be inevitable. Any fields that we can imagine must satisfy these conditions. Some of them will just be simplifying conditions. So I'll look for simple examples first, and then if I fail in my search for simple examples, though in fact I won't, we can imagine systematically loosening those conditions and looking for more complicated ones. Condition 1, there'll be 4 of them, is the condition I just wrote down, and I don't have to remind you of its motivation because I already said it in answer to a question. Our fields must commute for space-like separations. We will frequently have occasion to deal, not so much in this lecture, but in subsequent lectures, with non-Hermitian fields. Of course, only a Hermitian operator can be an observable, but sometimes it's convenient to sum together 2 Hermitian operators with an I in the summation to make a non-Hermitian operator. So I might as well tell you now that if I talk about a non-Hermitian field, I mean its real and imaginary parts are separately observables, or being quantum mechanics, I should say, its Hermitian and non-Hermitian parts are separately observables. So to take account of the possibility of non-Hermitian fields, excuse me, adjoint is also equal to 0 under the same conditions. That's just tantamount to saying the Hermitian and anti-Hermitian parts of the fields, all considered as a big set of fields, obey the first equation. The second condition I want to put on my fields is conditions on their space-time transformation properties. We know, in the specific case we're looking at, Fock space, we know how space-time translations and Lorentz transformation acts on the states. This should tell us something about how they act on the fields. Let's try and figure out what that something is. So there'll be a long argument on that, and then I'll write down condition 2 after I'm done with that argument. Let's think we can conceive of an operator-valued field in even in non-relativistic quantum mechanics. Suppose, for example, we have an electron gas or a Thomas Fermi atom and so on. We can think of the electron density at every space point as being a field, unobservable, an operator. It's a rather trivial operator, of course. It's the sum of a bunch of delta functions summed over the individual electrons. But it's an operator that's a function of space. And therefore, let's call this operator. It's a specific example. We can think of the electron density or the density in a gas, rho of x. X is not a quantum variable. It's just the point at which we are asking the question, what is the electron density? And if we have some arbitrary state psi, the expectation value of rho of x in that state psi is the electron density, and I'll call that function f of x. Okay, that's a situation we can imagine. We have some observable that depends on the point x, and I ask the question, in this state, what is the expectation value of that observable for a particular point x? Now, suppose we spatially translate the state. Suppose I define psi prime is either minus I p dot a psi. This is a state where I've picked up the whole box full of electrons and moved it over by a distance a. Now, what is the expectation value of rho of x in the state psi prime? Well, if there's any sense in the world at all, it must be f of x minus a. Perhaps that minus sign requires a little explanation. Suppose I plot f of x and just to take a definite example, let's suppose it's some function peaked near the origin. It's much more likely to find an electron at the origin of the coordinates than anywhere else. Now, I mean in the example. Now suppose I translate things by a distance a. So I'll mark that off here. Here's a. Of course, I'm assuming that I'm plotting a three-dimensional thing on a two-dimensional blackboard, but I hope you understand what is going on. The expectation value of f of x minus a is a function that is peaked at a if f is peaked at the origin. That is the right sign for moving the state over from being centered at the origin to being centered at a. And that's why there's a minus sign in this equation and not a plus sign. Okay, is that clear? Good. Now, of course, this is equal to psi UVI p dot a rho of x e to the minus I p dot a psi by the definition of psi prime. And since psi is an arbitrary state and a Hermitian operator is completely determined by its expectation value in an arbitrary state, we can eliminate psi from the right and left-hand sides of these equations and write e to the I p dot a rho of x e to the minus I p dot a equals rho of x minus a. Are there any questions about this simple exercise? This is simply the statement that the field at point, if you translate the fields with the translation operators in the same way you translate the states with the translation operators, I just went through the exercise so you would see where the sign came from in the front of the A. Okay, any questions? Everyone clear if I went too fast? We, of course, generalize this in the obvious way to relativity, where we have both space translations and time translations, to obtain our condition 2. E to the minus I, that's because of the minus sign I've perversely put in our metric, p dot a, phi a of x. Do not confuse a, the index, with a, the 4 vector that makes the translation. E to the I p dot a equals this expresses the spatial translation properties of our fields. By the way, this is in fact 4 equations at once for the 4 components of A. 3 of them, when A is a pure spatial vector, are of course just these 3 equations rewritten. The 4th one I got for you by generalization, but it should not be unfamiliar to you. The 4th equation, the one where A points purely in the time direction, is of course simply the integrated form of the Heisenberg equation of motion, since P naught is the Hamiltonian. Of course, I should have made that remark at the end of the last lecture or the beginning of this lecture. Of course, we are working in the Heisenberg picture. We must if we are talking about fields that are functions of both space and time, observables that are time dependent. That means we're doing Heisenberg picture. Okay, these are condition 1 and condition 2. Condition 3 will be just like condition 1, except it will express rotational invariance. If we have our electron density, of course, I can go through for rotations the same argument I went through for translations, and I would obtain rho of x, here instead of a translation operator, a rotation operator, And here I have rho of R inverse x. The R inverse appears here for the same reason the minus a appeared in the previous argument. If this is peaked at a given point, this is what is peaked at the rotated point. However, we know that this is not a unique law. For example, if we were to consider the gradient of the field rho, if we have any function of x, we can operator or otherwise, we can certainly take its gradient. That's just a linear operation. We would discover, as an elementary exercise, that's also a set of 3 operators for every spatial point. R grad rho of R inverse x, as you can easily work out by the chain rule for differentiation. This field we call a scalar field, and this field we call gradient a vector field, as you undoubtedly know from previous courses. Of course, gradients of scalars are not the only vectors. There are also all sorts of fields one encounters in classical physics that are vector fields that are not gradients of scalars, like the magnetic field, for example. And of course, one can go on, even considering rotations, and consider much more complicated objects, tensor fields, spinor fields, etc. However, the scalar field is certainly the simplest possibility, and therefore, for my third equation, I will assume my fields transform like scalars under Lorentz transformations. That is, I will choose to generalize the first of these equations rather than the second, and write this is a pure simplicity assumption. I could just as well have written down the transformation laws for a vector or a tensor if we knew how vectors and tensors transform under the Lorentz group, something we will investigate as time goes on, or spinors if we knew how spinors transformed under the Lorentz group. But this is certainly the simplest possibility, to assume all of our fields are scalars, and if it doesn't work, well, then we'll loosen it up a bit. So 1 and 2 are universal, and 3 is just a simplifying assumption. Certainly a consistent transformation law under Lorentz transformations, so it's the simplest one I can think of, so I'll try it. 4 is a super simplifying assumption. As was remarked in the question section, we have these A's and A adjoints floating around, so I'll make a very simplifying assumption. Phi A's are linear functions of AP's AP adjoints.
Are there any arguments in that? Why?
No, just pure simplicity. There are certainly many solutions where it is not so. For example, if I'm able to find a field that satisfies equations 1 to 4, I can make a vector field by taking the gradient of it, or a tensor field by taking the double derivative. I can make a field that's quadratic in the phi's and the A's and A adjoints by taking its square. Okay. These are strictly simplifying assumptions. 1 and 2 are absolutely essential. 1 and 2 are universal. 1 expresses relativistic causality. 2 expresses the fact that the x in the argument here translates as an x should. 3 and 4 are just plain simplifying assumptions, which I will make because they seem the simplest things to do. If I reach failure, then I am free to try erasing 3 and 4. I will not reach failure, but I mean, if I did, then I could try generalizing replacing 3 and 4 by weaker assumptions. Okay. And then if I couldn't find a solution at all, I would have to abandon the idea of fields. Okay, that's the logical position at this moment. The position of the logical position makes that sound like a value judgment. That is the position of the logic of the argument at this stage. Okay. Now, I will, I should ask, are there any questions about these four assumptions? Now I will, in order to exploit 1 and 2, 2 and 3, excuse me, I will have, well, in order to exploit all of them, I'll have to remind you of the properties of the A's and A adjoint. Right, memory of the previous lectures. You all remember, I hope, that A of P, A adjoint of P prime, equals delta cubed of P minus P prime. And all other commutators vanish. You will also remember that Lorentz transformation properties are expressed in terms of something. Unfortunately, since I've been giving away my notes, I don't remember whether I denoted it with a subscript or a P in parentheses before. In any case, I'll use a P in parentheses now. 2 pi to the 3/2 square root of 2 omega p A sub p, where p naught equals omega p. And then these objects had particularly simple Lorentz transformation properties. U of lambda alpha of p, U of lambda adjoint was alpha of lambda p, and likewise for lambda adjoint. They also have particularly simple properties under space translations, although I didn't bother to write them down, but they're very obvious. For example, if I were to consider e to the minus I p dot a, alpha of p, e to the plus I p dot a. Well, we know what alpha does. Suppose we apply this to any state. You might as well take the state to be a momentum eigenstate. This multiplies it by some phase. This knocks the momentum down. Put serifs on that so you'll remember it's the operator p, not the 4-vector p. This knocks the momentum down by an amount little p. This then puts in another phase factor which doesn't quite compensate for this one because the momentum has been knocked down, leaving us with e to the I little p dot a alpha of p again. By similar arguments or directly by taking the adjoint, we find e to the I p dot a alpha adjoint of p e to the minus I p dot a equals e to the minus I little p dot a alpha adjoint of p. Okay? Are there any questions on these equations or their derivation?
Could you go through the one before the last?
Sure. Well, I said, suppose I apply it to a momentum eigenstate. This multiplies it by a phase. This reduces momentum by amount little p. And therefore, this doesn't multiply it by a compensating phase, but a phase that's off by an amount little p. And that's just what I've written here.
Is the sign correct on the last question?
Yeah, I've adjointed the whole thing. Whoops, no, it is not. Thank you. I forgot that when I adjoin, I reverse the order. Yes?
Just the third one from the bottom, where you have the U of lambda alpha. Last time, I believe that you tried to demonstrate that.
Yeah.
Looking back at that, it wasn't clear to me that you had demonstrated that for every case.
Oh, this is something that should have been asked in the question session, but I will be happy to... Sure. If I take an n-particle state and apply U of lambda, I will show that it gives the correct transformation properties for an n-particle state. Okay? By definition, this is U of lambda, alpha adjoint of P1, one to n are, of course, not vector indices, but simply label the n distinct momenta. By the unitarity of U, I can insert a UU adjoint everywhere. And I can assert a U of lambda at the end because the vacuum is Lorentz invariant. Using my assumed valid equation, or more properly its adjoint, I observe that this is alpha adjoint of lambda P1, alpha adjoint of lambda Pn on the vacuum. Are you still with me? Which is lambda P1 dot 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 lambda Pn. Are you happy?
In other words, you make the assumption.
I've shown that this thing gives the conventional Lorentz transformation laws for the states. Okay? Equivalently, I could have said I take an arbitrary state, I act on it with this operator, and I demonstrate that the result is the same set of manipulations. You want me to do it that way? I take an arbitrary state, which is P1 to Pn. Okay? Okay, we'll do it again. Fine. Doesn't matter. Anyway, it's fine. No rush. I wish to find out what this operator is. I find out what it is if I operate with it on a complete set of states. Do you agree? The states P1 to Pn are complete. I use the fact that U of lambda adjoint equals U of lambda inverse, because U is unitary, equals U of lambda inverse, because these have the multiplication rules of the group. Okay? Therefore, this is U of lambda inverse, and therefore this is U of lambda alpha of P, lambda inverse P1, lambda inverse Pn, from the known Lorentz transformation properties of the states. You with me? I now apply, oh, I'm sorry, I should have made this an adjoint. Makes the argument simpler. Now I know what this does. It adds an extra particle with momentum P. Okay, I trust you will allow me to consider only the case where none of the P's are equal to, none of the PI's are equal to P. There's a square root of 2 otherwise, but okay. This is U of lambda P, one more particle, lambda inverse P1, etc. I know what this does to this state. This is lambda P, P1 to Pn, which I observe is alpha adjoint of lambda P, P1 to Pn. Since P1 to Pn is a complete set of states, I can remove it on the left and obtain the desired equation. Is that a more satisfactory argument? Good. Happy to oblige. Now, before this digression, I had written down these equations from the preceding lecture, and I will now use these equations and the 4 conditions to see how this field is restricted. I will use the conditions in reverse order. I will first use condition 4, then condition 3, then condition 2, and then condition 1 at the end. 1 is the hardest to check, so that's a reasonable way of doing things. Now, my penchant for clean blackboards, since I have cunningly put 1, 2, 3, and 4 on different blackboards. Will have to be, well, let me transfer 2, then at least I'll have a clean blackboard. 3 and 4 in those equations, I want to say. Now, from 4, phi is supposed to be a linear, the phi a's are supposed to be a linear function of a's and a adjoints. I will simply try and find the most general phi that is a linear function of the a's and a adjoints without putting an index a on it. If I find several solutions, then I can pick those several solutions to be phi 1, phi 2, and so on. So I'll just write as phi of x. By definition, it must be a linear function of the a's and a adjoints. There is no harm and much to be gained by putting in a factor of this form. And I'm sorry, I won't write phi of x. I'll just write phi of 0 at the origin of coordinates. Some function which I will call f minus of p alpha of p plus some function which I will call f plus of p times alpha adjoint of p. Since we're I want to, yes, you'll see. I do it now. You can't fault me for doing it, and I will show you we'll simplify later equations when we get to them. Where, of course, as always in such expressions, p0 equals omega p. So these are not really functions of 4 independent variables, but only of 3. F minus and f plus at this stage are arbitrary functions. So there's an infinite number of solutions to 4. There's an infinite number of linear functions of the a's of p's and a of p adjoints, which is, of course, not surprising. They're not restricted to be Hermitian, to be complex conjugates of each other. They are numerical valued functions because we are not necessarily looking for Hermitian fields yet. Now, from 3, I'm sorry, I'm going backwards. U of lambda phi of 0 U of lambda adjoint. Oh, no, that's not the way I wrote it. I wrote it that way. I'll stick with that way to avoid confusing people. Equals phi of 0, because lambda 0 is 0. To apply this equation, I use the fact that I have already remarked in my digressive remark that U of lambda adjoint equals U of lambda inverse equals U of lambda inverse. Therefore, I can apply the formula here and the identical one that holds for the alpha adjoints with lambda set equal to lambda inverse. Thus, I find phi of 0, the right-hand side of this equation, equals, well, the integral just involves C numbers so far. Two pi cubed 2 omega p. U of lambda goes right through that, like B through a baby. And then we have U of lambda on the f minus. That's just a number, so it goes through that. And then on the alpha p, alpha of lambda inverse p, because it is lambda inverse that we're applying, plus f plus of p, alpha adjoint of lambda inverse p. That's just a direct application of this equation and using the fact that a unitary operator is in particular a linear operator. Now, I define p prime equals lambda p, and I can rewrite my equation in terms of an integral over p prime. This integration has been chosen to be Lorentz invariant. When I switch from p prime to p, this thing doesn't change its form. That's the Lorentz invariant measure of lecture 1. So I have integral d cubed p prime over 2 pi cubed 2 omega p prime f minus of lambda p prime. Whoops. P prime, sorry, I did it wrong. P equals lambda P prime. F minus of lambda P prime, alpha of P prime, plus F plus of lambda P prime, alpha adjoint of P prime. The alphas and alpha adjoints are linearly independent operators. Therefore, if this is equal to this, the coefficients must be the same. And therefore, I deduce that F plus or minus of lambda P equals F plus or minus of P for any P and any lambda. Now, of course, the P's lie on the so-called mass hyperboloid, that curve I drew. And it follows from elementary relativity theory that I can get from any point on the mass hyperboloid to any other by a Lorentz transformation, by an appropriately chosen Lorentz transformation. So this, in fact, implies F plus or minus of P are constants. Which I will denote simply by F plus and minus without a P. Since they have the same value at any point as they have at any Lorentz transform point, and since any point on the hyperboloid can be reached from any other by Lorentz transformation, they must be constants. So 1 and 3 together have gone pretty far, at least as far as phi of 0 goes. We haven't talked about phi of x yet. 4 and 3 together have gone very far. We have reduced from the arbitrary functions in general linear functions, the scale statement that it transforms like a scalar has reduced us to 2 unknown constants. Any questions? Now, what about phi of x? Will that involve yet other unknown constants? The answer is no, because if I choose in this equation x equals 0, replace x by 0, and a by minus x, I obtain equals, I'm replacing x by 0 and a by minus x, easy I p dot x, phi of 0, e to the minus I p dot x, which of course I can compute since I have an expression for phi of 0. This thing equals integral d cubed p over 2 pi cubed 2 omega p f plus, f minus I had written first, alpha of p e to the minus I little p dot x plus f plus alpha adjoint of p e to the plus I p dot x. Therefore, even when I consider phi of x, I only have two arbitrary constants, f minus and f plus. Okay? I haven't used 1 yet. This is the most general. I have, of course, not used all of 2, 3, and 4. For example, I used 3 just at the point 0, not at a general point. But it is trivial to check, and I leave it as an exercise for you, that every expression of this form satisfies 2, 3, and 4 for all x and all a. You can almost read it off, I think, from what we know. Are there any questions whatsoever? Yes, sir.
You had the I p dot x on one side, minus I p.
Don't forget I'm setting a equal to minus x. So a is minus x here, a is minus x here, and a is minus x here. That's where I got an e to the minus I p dot x.
No, I'm saying you have them on both sides on the equation below, and you somehow cancel one of them.
No, this is the operator P, and I'm using this equation where they are on both sides on the left.
Oh, you know. You're evaluating alpha.
Yeah, sure. I'm using exactly as for the U's. All of these things are just C numbers, and the exponential goes right through them, and then it just acts on alpha of P. Okay, is that clear? Okay, these are non-numbers. The only operators left in these equations are alpha and alpha adjoint. Okay. So let's summarize the situation before we apply 4, before we apply 1. I erased the delta function commutators, which I'm going to use shortly, but you all have them in your notes several times. Summary. A general field satisfying 2, 3, and 4 is the sum of two independent fields, which I will call phi minus and phi plus, where f plus and f minus are arbitrary numbers. Phi minus and phi plus are, of course, the coefficients of f plus and f minus down there, but I'll write them down once more, and I'll write them in terms of not the alphas but the a's, since it's easier to compute commutators using the a's. Phi minus is integral d cubed p, since there are all those square roots and that going from the alphas to the a's. I get 2 pi to the 3 halves, square root of 2 omega p. A sub p e to the minus I p dot x. Phi plus equals integral d cubed p 2 pi to the 3 halves square root of 2 omega p, same thing. A sub p adjoint e to the plus I p dot x, and as usual, when the 4 vector p appears, its fourth component is its time component is omega p. Phi minus and phi plus are, of course, Hermitian conjugates, and perhaps I should write that down. Yes, sir.
Why is there 3 halves?
Because there was a 2 pi to the 3 halves in the definition of the alphas in terms of the a's. The alphas were 2 pi to the 3 halves square root of 2 omega p. Okay, I've just plugged in things in terms of the a's. That'll make it easy for us to compute commutators later, because now we've just got objects with simple delta function commutators, so we don't have to worry about Lorentz normalization factors. We don't have to remember them. They're all summed up here. Now, we have two possibilities. We really only have, this is the most general solution, but we really only have two possibilities. We could say all of these things are possible observables for any value of f minus and f plus. But of course, if we have anything that satisfies condition 1, any linear combinations of things that satisfy condition 1 will satisfy condition 1. Therefore, we have two possible possibilities. Possibility A, phi plus and phi minus as a set. Jointly, I'll write, you mean as a set. Satisfy 1, in which case any linear combination of them will satisfy 1. In that case, we would have two independent fields, which could be thought of as either phi plus or phi minus, or as the Hermitian and anti-Hermitian parts of either phi plus or phi minus. Alternatively, possibility B is that only one Hermitian linear combination of them satisfies condition 1. And of course, the most general Hermitian combination is, aside from a multiplying factor, which is irrelevant, some complex number which I choose to have magnitude 1, plus another complex number which I choose to have, which must have the conjugate magnitude, so it be Hermitian, satisfies 1, but the individual parts don't. I've got to take conjugate combinations, because if I don't, then of course by taking the Hermitian and anti-Hermitian parts I would get back to possibility A. So either we have two fields or we have one field, and if we have one field it must be of this form, so it is Hermitian. Actually, we can shorten our work a bit by realizing that we can get rid of the phase factor by redefining A of P where theta is the number up there. If we make such a redefinition, that changes no equation we have written on the board until then and absorbs the factor theta into the A's and the A adjoints. So therefore, I might as well consider equivalently B prime. All the algebra will be the same, just the Hermitian part of phi plus. So therefore, we really have only two independent possibilities to consider. Possibility A, in which we say both phi plus and phi minus are local, and possibility B prime, in which we say just the sum is the observable thing and the difference is not an observable thing. Okay, any questions? Now we will systematically look at these two possibilities. Obviously, A is the one we should look at first, because everything we have to compute check A, we also have to compute to check B. So we investigate A. We want to see everything commutes with itself for space-like separations. Everything means phi plus with phi plus, phi minus with phi minus, and phi plus with phi minus. Well, phi plus with phi plus, space-like, schmace-like, they all involve nothing but creation operators, the phi pluses, and therefore all creation operators commute with each other no matter what we multiply them by, so that's 0. So that's okay. By similar reasoning, or by taking the adjoint, the same thing goes for phi plus with phi minus with phi minus. Now we come to the crunch, and here I'm going to introduce a function that has a standard definition. Phi minus, so I better get things in the right order. Let's compute phi minus of x with phi plus of y. Well, we can sort of eyeball it. It's going to be a double, this is an integral d cubed p, and say this is an integral d cubed p prime. But the only commutator is an a with an a adjoint, which is a delta function. So that'll collapse to a single integral d cubed p. So we'll have a single integral d cubed p. From here we have a 2 pi to the 3 halves, and from here we have a 2 pi to the 3 halves. So that's 2 pi cubed. From here we have a 2 omega square root from both places, but p is equal to p prime. So that's 2 omega p. And from the first term we have an e to the minus I p x. And from the second term we have it with a y in the opposite sign. And that's everything. Computed the commutator. That just comes from the AFP adjoint with AFP commutator being a delta function. That enables me to do the integral in one line. This function will turn up again and again in our investigations, and it has a special name. It's actually a Neumann function or something, I think, but it has a special name in field theory. It's called delta plus. It's a function of x minus y only, as is obvious from the expression, and it depends on the mass mu squared via the definition of omega p and also what p naught is. For short, we'll just, as long as we're only worrying about one mass, to keep our equation short, I'll just call it delta plus of x minus y. If we were worrying about several kinds of particles with different masses, we would have to distinguish between the different delta pluses. Now, this is the commutator we want to vanish for space-like separations. And therefore, the question we want to ask is, oh, before I ask that question, sorry. One nice thing you would expect to be true of delta plus, and which is indeed true from this formula, since this is come together again to make the Lorentz invariant measure, is that delta plus is a scalar function. That is to say, delta plus of x equals delta plus of lambda x. And that will be a useful fact to us later. But the real question we want to ask now, the check, to make sure the commutator vanishes at space-like separation, or doesn't, is delta plus of x equal to 0 if x squared is less than 0. If it is, we're home free. Otherwise, we have to look at possibility B. Now, it doesn't. How do we know it doesn't? We know it doesn't from lecture 1. Because if I take the time derivative of delta plus, I get precise, that cancels out the omega p in the denominator, and I get precisely the integral I had to consider in lecture 1 when I wondered whether particles could travel faster than light. Now, if a function vanishes for all space like x squared, its time derivative surely vanishes for all space like x squared. By the explicit computation of lecture 1, its time derivative doesn't vanish, so the function don't. And the answer to the question is no. From lecture 1, d naught delta plus not equal to 0 for x squared less than 0. We found the particle traveling faster than light, and that was the same integral. Never waste a computation. Okay? So delta plus doesn't vanish, and possibility A gets thrown into the garbage pail. Therefore, we turn to the only remaining possibility, which is possibility B. Is everyone with me so far? If possibility B is also gets thrown into the garbage pail, not only this lecture, but this entire course will end in disaster. But at this stage, that's a logical possibility, in which case we would have to worry about weakening 3 and 4, as I say. Well, phi of x, b. Here we only have one field, so we only have one commutator to check. That's the question. Now, fortunately, since this phi is phi plus plus phi minus, the commutator is the sum of 4 terms we have already computed. Phi plus here with phi plus here gives 0. So that's 0. Phi minus here with phi minus here gives 0. The minus with the plus gives us delta plus of x minus y. The plus with the minus gives us a minus sign because the commutator is switched around. And y minus x, because the y is now the minus and the plus is now the x. This function also has a name. It's going to come up again and again. It's called I delta of x minus y, with the mass inserted, of course, if we want to keep track of what the mass is. I've been very careful, by the way, in defining these functions, for which the definitions vary from text to text, to stick to the conventions abused in Bjorken and Drell. Now, therefore, for here, our question is, reduces to, is delta of x equal? We will explore, for what may seem to you an infinite length of time, the free scalar field. The homework problems all involve it. Phi of x equals integral d cubed p 2 pi to the 3 halves square root of 2 omega p a sub p e to the minus I p dot x plus a sub p adjoint e to the plus I p dot x. This is the free scalar field, and of course, as before, p naught is always equal to omega p. Now, we take off in a new direction. Several times in our course of development, we have introduced objects in the first instance as auxiliary objects, like the annihilation and creation operators, and then showed that the whole theory could be defined in terms of their properties. I would now like to show that the whole theory can be defined in terms of certain properties of this free scalar field, but I will have to derive those properties. The two properties, one of them we already have and the other one is trivial. The trivial one is that this obeys a differential equation. And that differential equation is this. This is just a statement that in Fourier space, p squared equals mu squared. If I differentiate twice with respect to x, I replace this. The IP gives me a minus p squared, which is equal to mu squared because p naught is omega p. The second equation is one we already have. Where that is some well-defined function defined by this integral expression, and delta minus is, sorry, did I write delta plus? That is a hideous error, I delta. And delta is defined as delta plus over there. Now, does anyone doubt these two equations? Yes, sir.
I don't see where the fact that x squared is less than 0 comes in.
Because if I have a time-like vector, I cannot, which lies on the upper hyperboloid, I cannot turn it into minus x, which lies on the lower hyperboloid by Lorentz transformation. That's a good thing, because if there were such a Lorentz transformation, then Lorentz invariance would imply that you could travel backwards in time if you can travel forwards in time. Okay? And would be an evident contradiction with observed reality. Delta doesn't vanish for time-like separations. Well, in fact, we'll shortly compute it for a particular time-like separation. We'll compute it at the tip of the light cone, to be precise. There's a historical note which goes with the first equation. The first equation has a famous name. It is called the Klein-Gordon Equation. As you might guess from the name, it was first written down by Schrödinger. But he didn't know what to do with it because he wrote it down as a relativistic analog of the free Schrödinger equation. And then he said, arg, or the German equivalent, because by solving this equation, he observed that its solutions had both positive and negative frequencies in them. And he said, if this is a one-particle wave equation, we are in the soup, because we only want positive energies. We don't want negative energies. We have encountered this equation not as a one-particle wave equation, in which context it is really garbage, so that equations 1 and 2 sketch out that equations 1 and 2 completely define the Hilbert-Fock space and everything else, and therefore the scalar field, which we have introduced as an auxiliary variable, we can just as well think of as an object that defines the theory. We start with 1. Okay, I'll sketch the argument. From 1, we can write this equation up here as a definition. This is the most general expression. The top equation becomes the definition of AP and AP adjoint. This is the most general expression for a solution of this equation with unknown Fourier coefficients. Its Fourier transform will either contain only vectors on the upper hyperboloid or only vectors on the lower hyperboloid, and there they are. We also know that, sorry, I should have written the third equation. Phi is Hermitian. Important. From the fact that phi is Hermitian, we know the coefficient here is the adjoint of the coefficient here. So we can use equation 1 and the hermiticity of 3 as our starting points to define A and A adjoint via the equation on the top of the board. Once we've defined A and A adjoint, we could deduce their commutators uniquely simply by Fourier transforming this equation. If we know the commutator of phi of x with phi of y for any x and any y, we certainly know the commutators of the Fourier transforms for any p and any p prime, and therefore we deduce the commutators of A and A adjoint. We can also deduce the so we have A's and A adjoints, and we can uniquely deduce their commutators. Once I have observed that it is unique, I don't have to go through it because we already know one equation that is consistent with everything on the board. It is the delta function commutators. Finally, from the general condition on a field that phi of x minus A equals, I don't remember it, so I hope I'm writing it with the right sign. Yeah. We can deduce from this equation the commutators of the A and A adjoints with the p's and the E and the Hamiltonian, simply by differentiation, because by differentiating this, we know the commutator of phi with the Hamiltonian, or the momentum operator, and by Fourier transform, we know therefore we know the commutators of the A and the A adjoints with the momentum operator and the Hamiltonian. This tells us that A adjoint is an energy raising operator and A is an energy lowering operator, and off we go, as in the middle of the previous lecture, reconstructing all of Fock space on this principle. So that was a sketch, not a proof, but I leapt from mountain peak to mountain peak without going through the valleys, but I hope the logic is clear. Everything comes from the A's and their A adjoints, their commutators with each other, their commutators with the Hamiltonian and the momentum operator. And from these equations, we can define the A's and the A adjoints via this, deduce their commutators from this, and deduce their commutators from the Hamiltonian and the momentum operator from this. Of course, this does not give us a zero of energy, but that's just a matter of, because if all we know are the commutators, we don't know what the ground state energy is. But we can always define that by convention to be zero. Yes, sir? Yeah, it comes from the zero component of this. You differentiate with respect to A0 and you get the commutator. Now, This is not all. We go on. Unless someone screams, shouts, halt, you're going too fast. We go on. Because 2 can actually be weakened. In fact, we know the commutator can be replaced by 2 prime, which comes in 2 parts. 2 prime is simply specifying phi of x and t with phi of y and t equals something, which I'll compute in a moment, but it's some definite function, which we can compute. And also computing phi dot, where dot is always means time derivative, d naught, equals something else. Again, some numerical function, which we will shortly compute. Why do I say this? Why do I say that 2 can be replaced by 2 prime? Well, it's because the Klein-Gordon equation is a second-order differential equation in the time. Therefore, just from the Klein-Gordon equation, from this fact here, from 1, I know differentiating only on the variable y, considering the variable x as fixed, x is fixed, the commutator is a linear operation, therefore I just bring the del squared through and use the Klein-Gordon equation. Now del squared equals d naught squared minus grad squared. This is a second-order differential equation, and you know the solution of a second-order differential equation for arbitrary values of the argument if you know its value and its first time derivative at some fixed time, the initial value conditions. Here is the value of this thing at a fixed time. The time of the y variable equals the time of the x variable. Here is the first time derivative at a fixed time. It's the same fixed time. Therefore, you integrate away, as in all books on differential equations, and you know the solution uniquely. Therefore, we in fact do not need to write down this messy Fourier transform, delta. We only need to write down these 2 things. We only have to compute something and something else. Then that will be sufficient, because we know this thing obeys a second-order time derivative equation to compute delta at all times. We don't have to specify it. It's specified by consistency with condition 1, the Klein-Gordon equation. People are looking blank. Don't look blank. Ask questions. Yes, sir. What? No, yt. I have to know this for all y at a fixed time, a second order in the time. I have to know it for all values of the space variable at a fixed time. Then I integrate forward from the initial value surface, t prime equals t. Yeah.
Shouldn't that commutator be 0?
Well, we're going to compute it. Something is going to be 0, and something else is going to be something else. Okay, but at the moment, I wanted to tell you why they should be computable. Yes, in fact, something will turn out to be 0. It's not clear. It doesn't come, well, you could say it comes from locality, because these are all space-like points, aside from x equals y, when the thing commutes with itself. But that's a little bit tricky. It could involve something like the derivative of a delta function or some other obnoxious object. We'll directly compute it and find out what happens. It's certainly, something and something else are certainly going to be combinations of delta functions and their derivatives, because this is a property we already know from locality that these things must commute for x not equal to y. Yes? Well, yeah, I'm going to compute it. Okay. 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 Yeah. Now I remind you, I don't have to remind you, it's right here, the necessary commutator. We just have to reduce it to equal times. And therefore, I'll just write down the expression for I delta. Over 2 pi cubed, 2 omega p, e to the minus ip, x minus y, plus e to the plus ip, x minus y. And it's not plus, it's minus. Okay, I've just plugged in the Fourier transform definitions of delta plus and written down an explicit expression for delta. These are 4 vectors. Our scheme is to evaluate them at equal times. Well, the first one at equal times is pretty easy. This is a pure spatial vector, and this is minus the same pure spatial vector, and therefore the 2 integrals are equal by rotational invariance, and they subtract from each other, so something is, as anticipated, 0. Now something else. Well, that one's a little more complicated, because when I differentiate with respect to y here, the time component of y, I'll bring down a p naught, which is a minus I omega p. And here I'll bring a plus I omega p, minus times minus. And here I'll bring down a omega p with the opposite sign, therefore canceling the effects of the minus sign. Therefore, the 2 terms in this expression give me equal contributions, which I will take care of by writing a 2. I have integral d cubed p over 2 pi cubed 2 omega p. I have brought down an I omega p from my time differentiation with respect to y. And I have left the exponential where the time coordinates are equal, so that it's plus ip dot x minus y. Is there any question about how I derive this equation by this? I tend to go fast when I'm doing computations, because I feel that if it's too fast for you, you've got it all in your notebook and you can figure out the steps yourself. But it should be obvious. I just differentiated with respect to time. Now, this integral is not strikingly difficult to do, because the 2 up here cancels the 2 on here. The omega p here cancels the omega p down here, and this is revealed to be I delta cubed of x minus y. That's a much simpler function than capital delta, which, as I said, is in general a terrible Bessel function. And as I've argued, 1, 2' A, 2' B, and 3 are sufficient to reconstruct the whole theory. So we've got the whole theory in terms of those things. The field, to summarize, the field which we have introduced as an auxiliary entity, in fact, not only gives us a definition of locality consistent with the dynamics we had before, but all the dynamics we had before can be expressed in terms of the field. The fact that it obeys the Klein-Gordon equation, the fact that it is Hermitian, and this equal time commutation relations, these particular equal time commutation relations. The homework problems have you playing with these equations to develop certain identities that will be useful to us later on in the course. Now, are there any questions at this stage? Because I'm now going to go on. I'm now going to go into mystic and visionary mode and remind you that these equations look very similar to some equations we have encountered before in non-relativistic quantum mechanics. But before I do that, yes, sir, a question.
You said 2' A and B earlier are actually weaker than 2?
No, they're equivalent to 2, but they look weaker. They're equivalent to 2, but you give much less information because a lot of the information that's in 2 is in fact can be deduced from 1 and 2' A and B. 2' A and B are weaker than 2. 2' A and B plus 1 is equivalent to 1 plus 2. Now, what are these equations remind me of something. What they remind me of are following equations you might have seen before. Remember good old canonical quantization and canonical commutation rules for non-relativistic quantum mechanics. This is my mystical visionary mode. It's going to develop some clues. We have these equations for the Heisenberg field operators in non-relativistic quantum mechanics. There's normally an h-bar in this equation, but I've set h-bar equal to 1. And in fact, there's a third equation that comes with them. Now, those equations bear the first two of these equations bear a certain structural similarity to the equations I have on the top of the board. If I identify phi dot with P and phi with Q. It's true instead of a discrete index A, labeling the various coordinates, I have a continuous index, X and Y, replacing A and B. And as a consequence of that, instead of a Kronecker delta, I have a Dirac delta function. But otherwise, they look very similar. To test that vague similarity, let me try and compute the analog of the third equation. If I identify P with phi dot in the system, I would have to compute phi dot of x and t, phi dot of y and t. Well, this is the same computation as before. I have two time derivatives. So from this factor, I get an omega minus omega p squared. And from this factor, I get exactly the same thing because it's two derivatives, so the sign of p naught doesn't matter. And then just as it's phi with phi dot with phi dot, the two terms cancel, equals 0, which looks awfully like the third equation. Therefore, there seems to be some vague connection with the system we have developed without ever talking about canonical equal time commutation relations and the canonical quantization method. Maybe. Or maybe I'm just dribbling on at the mouth. But there seems to be a certain suggestive structural similarity. Now, I would like to, in the next lecture, and I won't start at this lecture, I'll let you off early because I want to go to a seminar at 4 and have a moment to breathe beforehand. But in the next lecture, I will exploit that similarity in a much more systematic way. It's going to take 2 or 3 minutes for me to explain what that systematic way is. I will develop this entire system we have on the board, which we have developed by one method, by a completely different and independent line of approach that leads to the same answer. This method will be the method of canonical quantization, or as I like to describe it, as I will describe it somewhat colorfully, the method of the missing box. And I will explain what I mean by the missing box. I'm going to put some boxes on the board. This is classical particle theory, the theory of Lagrange and Hamilton, which you all know, but which at the beginning of next lecture I will review the general parts of in my characteristic lightning fashion. We also, you may or may not know, that of course you can generalize classical particle theory to systems with an infinite numbers of degrees of freedom, or a continuous, even a continuous infinity of degrees of freedom, and write down Hamiltonians and Lagrangians for classical field theories. Therefore, by going this way, passing to infinite degrees of freedom, one gets classical field theory, the classical theory of Maxwell's equation, of sound waves in a fluid, of elasticity in an elastic solid, the classical continuum theory. You also know, I hope, if you've had a good course in non-relativistic quantum mechanics, or in particular if you took the course from me last year, that there is a standard procedure from getting from classical particle theory to quantum theory, which I will also review next lecture, called canonical quantization. Just to remind you of what it is, I'll say it in great detail. It says you write the system in canonical, in Hamiltonian form, and you put commutation relations between the classical P's and Q's. This leads to quantum particle theory. I presume these three boxes are familiar to you. I will give brief summaries of them, complete but fast, in the first half of next lecture, if they are not. What we will attempt to do in the second half of next lecture is fill in the missing box, which at the moment I don't think you know anything about, or I pretend you don't know anything about, which is obviously quantum field theory. As the arrows show, it can either be viewed as the result of applying canonical quantization to classical field theory, following this arrow down, the language of the algebraic topologist, this is a commutative diagram, or by following this arrow across and generalizing quantum particle theory to systems with an infinite, continuous infinity of degrees of freedom. Next lecture, I will fill in the missing box, and we will arrive at the same system we arrived at by another means.
Fundamental relationship between translation and
Which what? No, why not a delta double?